Hello, AP Chemistry students. In this video, we are going to cover Notes 7 and Notes 8, which cover intermolecular forces, or IMFs, and their properties. So far in this unit, we've really covered something called intramolecular forces, which are the attractive forces within a molecule, and these are bonds. Okay, we've done Lewis structures, and we've been able to tell if a molecule is polar or nonpolar, and that was all within a molecule. And now we're going to talk about intermolecular forces, or the attraction between molecules. Intermolecular forces are not bonds. Okay, they are just attractions, and they're going to be very important with different phase changes in physical properties that we see with our molecules. It is important that you know, and I'm going to say it again even though I've already said it, that intermolecular forces are not bonds. This is certainly going to be a test question because we are in the bonding unit. A lot of people like to think that intermolecular forces are bonds, but they are just attractions, and they are not actual chemical bonds. There are four major types of intermolecular forces, and here they are listed, and I'm going to go through each of them. But before I do, I just want you to put a star next to ion dipole. And ion dipole forces are stronger than London dispersion forces, dipole-dipole, or hydrogen bonding, but they're very uncommon. They're uncommon because they only exist if you have a mixture. Not all mixtures, but they have to be in a mixture. And generally, when we're talking about intermolecular forces, we are discussing pure substances. And pure substances only have one type of particle. And when you only have one type of particle, you could never have ion-dipole interactions. Generally, LDFs are weak. And hydrogen bonding, which you may remember that terminology from last year, are generally strong. An ion dipole would technically be stronger than hydrogen bonding. I will wait upon my return to go over ion dipole in more detail, okay? Although LDFs are generally weak and hydrogen bonding is generally strong, this is not always the case, and so we're going to go through each of them and talk about when there may be exceptions to these rules. If you look, London dispersion forces, or just dispersion forces, generally weak. Dipole-dipole, a little bit stronger. Hydrogen bonding, even stronger. And you can see ion dipole is generally going to have a little bit of an edge out over hydrogen bonding. We can see that these are generally weak because the forces of attraction in units of kilojoules per mole are somewhere between like 1 to maybe 20 kilojoules per mole, where covalent bonds are going to be in the 300 to possibly even approaching, 800 kilojoules per mole, which is a huge order of magnitude stronger, okay? So these are bonds, intramolecular forces, and intermolecular forces are just attractions. Okay, these are chemical bonds if they're intramolecular forces. Attractions are not chemical bonds. Okay, so we're going to skip over ion dipole for just right now, and I'm going to summarize. You should have a page here in your notes packet, what I think is important for you to know about intermolecular forces. So the first one is London dispersion forces, which we can commonly abbreviate LDFs. These are sometimes called just dispersion forces. And less common, but still could show up on the AP test, they might be called van der Waals. But in my classroom, I'll just refer to them as LDFs. That's generally the agreed upon terminology. Now, London dispersion forces are present in every molecule. And they're present in every atom. They're generally weak, but they can become strong. So let's talk about when they would become significant. They're going to become significant in large atoms or large molecules. So, a general rule of thumb is that if you have more electrons, that's going to equal more London dispersion forces. So, for example, we could compare itty-bitty helium versus a little bit larger neon on the periodic table. They're both noble gases. Neon, although it's larger, neon has more electrons, and so this has stronger LDFs. And then we're going to get into what that means as far as properties. So stronger LDFs, this is just kind of getting ahead of myself, but they're going to have a higher boiling point, a stronger surface tension, higher viscosity, things of that nature. So what is a London dispersion force? It is simply electrons in one atom attracted to the nucleus. Remember, the nucleus is positively charged of another atom. So, for example, let's say I just draw some kind of element with two energy levels, and we have electrons here, and this electron is attracted to its nucleus, and that's not an LDF. But you never have just one atom. Atoms are so small that even in the smallest sample, you'd have at least 1 million. And there's maybe another atom and although the nucleus is further away, that electron is still attracted to any kind of positive charge, and this is the LDF. So again, it's electrons in one atom attracted to the nucleus of another atom. They are present in everything, in every molecule and in every atom, because every sample is going to have electrons and every sample is going to have atoms that have a nucleus. Okay. Now, our next one is going to be dipole-dipole. And dipole-dipole interactions are generally strong. And dipole-dipole is present only in polar molecules. Okay, and if you remember from polar molecules, you'll have a delta positive side of your molecule, and then you'll have a delta negative side of your molecule. That's what dipole means. So delta positive in one molecule attracted to delta negative in another molecule. And so if I think of an example, let me think here of we could have a molecule like cyanide. Looks like this. And with cyanide, carbon's 2.5, nitrogen's, not 2, but 3.0. And so we could say that nitrogen's delta negative, carbon's delta positive, and we could have a dipole arrow pointed towards nitrogen. Nothing cancels out that dipole arrow, so that makes that molecule a polar molecule. And so how other cyanide molecules will interact around this is that you have two options. You could have carbon and nitrogen like so, or you could have them arranged nitrogen then carbon. Well, if we remember that carbon here is delta positive, where nitrogen's delta negative, two delta negatives are actually going to repel each other. That's not going to be any kind of attraction, and so that's not going to happen. And so what actually happens is opposites attract, kind of a big idea in chemistry. And so this is your dipole-dipole. Okay, notice that we get arrows kind of pointing in one direction, and this is your dipole-dipole attraction. Okay. So let's now look at hydrogen bonding, our very last one for this set of notes. Hydrogen bonding can be abbreviated H bonding. And it's generally the strongest type that we'll mention. First of all, though, because it's an intermolecular force, it is not a bond. I understand it says bond, and whoever named that did a poor job, but it's not a bond. Rather, it's a attraction. I always teach that hydrogen bonding is not fun, but it's fawn, meaning you need F, O, or N bonded to hydrogen. And it's simply just extreme dipole-dipole. So if you can understand dipole-dipole with delta positive attracted to delta negative, hydrogen bonding is the exact same thing, but instead of it being delta positive and delta negative, it's like a very large delta positive and a very large delta negative. And so here's what we see. We see when H is bonded with F, let's say H is bonded to O and H is bonded to N, hydrogen has an electronegativity value of 2.1. And again, you would be given those electronegativity values on a test, on a quiz. Fluorine is the most electronegative element at 4.0. Oxygen is second most at 3.5. And nitrogen is the third highest electronegativity value at 3.0. And so we can see that hydrogen and fluorine, their bond is so polar, has a difference of 1.9. Hydrogen and oxygen has a difference of 1.4. And nitrogen and hydrogen have a difference of 0.9. Those are very large differences. And so what we get, if I take these, is we get huge delta negatives and delta positives. So we get delta positive, delta negative, a little bit less delta positive, but still very strong, delta negative, even less, but still strong, and delta negative. And so HF, if I use that as an example, will line up just like cyanide will, where opposites will attract. But we have delta negative and then delta positive, and this is your hydrogen bond. And because those are such strong delta positives and delta negatives, very large, this is a very strong dipole-dipole interaction, and we call that hydrogen bonding. It is annoying, but I want us to make sure that when we see H covalently bonded to F, this is not an IMF, and therefore it's not a H bond. Okay. But when we see this, we can know that hydrogen bonding is present, and so we're going to see that on the next set of notes. Okay, moving on to notes 8. Notes 8 should not take very long here. There's a lot to read through, but here's what you know, is that gas particles, we can arrange them like so, and then liquids a little bit closer together, and solids very compact and high attraction. So because our solid particles are very close together, there's large attraction. And gas particles, if you remember from Unit 3, gas particles are so far away from each other that their IMFs, according to kinetic molecular theory, we said that they're very low or even non-existent. So we could say very low / no attraction. They're so far apart from each other that they don't even know that the other particle exists. And so if we have large attraction, this is going to be strong IMFs. And if we have very weak to no attraction, this is going to be weak IMFs. And the stronger your intermolecular forces, the more likely your particles are to stick together. Okay, so what I need you to know is that strong properties equal strong IMFs. So if you can identify that something has strong IMFs, you will then know that it has strong properties like boiling point, freezing point, melting point, viscosity, surface tension. There is one exception, and we'll go ahead and write that right now. And there's only one exception. And I can't spell, goodness. That one exception is vapor pressure. Later in this video, we'll go through vapor pressure. So, if we look here at C8H18, C6H14, C4H10, and I have an organic line drawing here. We're going to learn how to do those a little bit later in this unit. But hydrocarbons, and let's say true hydrocarbons, so that's C some number, H some number. A lot of hydrocarbons have oxygen and nitrogen in them, and they're still hydrocarbons, but let's not call them true hydrocarbons unless they're only carbon and hydrogen. True hydrocarbons are always nonpolar. Okay, so all of these have LDFs. And if we remember from the last set of notes that we just went through is how do we determine which has more LDFs? And because if something had hydrogen bonding or dipole-dipole, we would easily be able to say, oh, that thing has maybe the higher boiling point. But here, we might not be able to tell because they all have LDFs, but we can remember that more electrons equals stronger LDFs. Thus, C8H18 with more atoms, significantly more atoms, is going to have more electrons, and we see that its boiling point is 125 degrees Celsius. That's octane. You may be familiar with octane. Where butane, which is in like butane lighters, the lighters that we've used to light Bunsen burners, has a boiling point of -1 degrees Celsius. Even though they're all nonpolar, LDFs can become significant when you get large molecules. Distillation we will do later. If you take organic chemistry, you'll definitely do distillation, but it is a process by separating a mixture based on boiling points. Okay, we will talk more about this later, and the good news is it's not on quiz or the test. Surface tension. This one probably is on the quiz or test. So surface tension is the resistance for a substance to increase in surface area. The example that I always use because it just is something that kind of resonates with me is, have you ever seen like a small insect or a bug walking on water? So I'm going to draw a bug. I know it's not going to be a great little picture here, but I have my bug. And my bug is walking on water. So somehow these water particles are able to hold themselves together, and the reason why is water has hydrogen bonding. Oops. And so what I can draw is hydrogen bonds that hold the water particles together. This bug, the force exerted down, the force of the bug must be small or smaller than the force of the hydrogen bonds holding the water together. If you take something like, I don't know, a rock, which is going to have much more mass and therefore a larger force on the water, the rock will probably be able to break the surface of the water because the rock's force will overcome the hydrogen bonding and it will break. When you break hydrogen bonds, this is not a chemical change. This is simply just breaking intermolecular forces because, of course, if we throw a rock in water, the water's not undergoing a chemical change. The water is still water. We've just broken the hydrogen bonds. Now, vapor pressure, and why it has the asterisk, is that it is the one exception. So, vapor pressure is the pressure of a substance in the gas phase above, generally it's liquid phase or solid phase. So strong IMFs generally lead to strong properties except with vapor pressure. So if I have strong IMFs, let's imagine I have something that's a solid and it has strong IMFs. Here's what that means. That means that the particles are strongly attracted to each other. And if they're strongly attracted to each other due to these strong IMFs, it is going to become difficult for one of these particles to escape and enter the gas phase. Thus, weak IMFs equals weak attraction. And if it has weak attraction, it's going to be more likely for something to enter the gas phase. So imagine we have something here where the attraction is generally weak. It will be easy for one of those particles to absorb heat from the surroundings and enter the gas phase because this attraction is weak. And therefore, things that have high vapor pressure have weak IMFs. This is why if you've ever filled up your car with gasoline at the gas station, you probably have smelled gasoline. Gasoline, I'm not saying that it's truly a hydrocarbon, but it's generally hydrocarbons, and like there might be octane in your gasoline, for example. And we know from the previous page that octane is C8H18. Well, granted, octane is a hydrocarbon, and so it only has LDFs, and it may have stronger LDFs than other hydrocarbons, but still it just has LDFs, which are weak intermolecular forces. So it's very possible that one of the gasoline molecules or octane molecules can escape into the gas phase easily. And that's why we're able to smell gasoline generally when we go to the gas station, because some of those particles have left the liquid phase, and they've entered the gas phase, and then we are able to smell them. Okay. I'm going to go ahead and I'm going to go through these practice questions on the next 2 pages. I'm going to give you the Lewis structures here. I trust that you're able to do your Lewis structures, and so I want to just be able to move past that. Here is CO2. You can go ahead and draw that. I'm going to go through many of these. Here is OCS. Here is PF3. Here's PF5. Okay, go ahead to make sure you're taking a second, just copying these down. Here is SO3. Here is SO2. Here is HF. Here is HBr. Here is CH3OH. Here is H2CO. Okay, and then I'll talk about F in just a second. So, the question is asked of us, and it says, predict which substance from the following pairs would have greater intermolecular forces and explain. Well, this could also ask, the question's asking greater intermolecular forces. This could say which one has a higher boiling point. It could say melting point, freezing point, viscosity, surface tension, and we could go on and on and on, okay? Greater intermolecular forces mean higher of all of those things except vapor pressure. So what you want to do is the Lewis structure is going to help you out with the geometry, and the geometry is going to help you out whether or not something is polar or nonpolar. So do me a favor, pause the video, and go through and label each of these as polar or nonpolar. And before you pause, I forgot a lone pair on this phosphorus. I apologize about that. Okay? So pause the video, label each of these molecules that I've drawn as polar or nonpolar. Okay, so when something is nonpolar, we instantly know that it has only LDFs. When something is polar, it has LDFs and dipole-dipole. When something has dipole-dipole, dipole-dipole is generally stronger than LDFs. Therefore, in this first example, OCS will have greater intermolecular forces. If you're curious, a dipole arrow will be pointed in this direction. The same thing is true for PF3 versus PF5. Although PF3 is a smaller molecule, they both have LDFs, PF5 is going to have more LDFs. Okay, just larger molecules mean that it's generally going to have more electrons, and more electrons means more LDFs. And with PF3, though, being polar, it is going to have dipole-dipole, and dipole-dipole is generally going to outweigh LDFs. Therefore, PF3 is going to have stronger intermolecular forces. Not stronger LDFs, but a stronger total amount of intermolecular forces. Dipole arrow would be pointed up. Okay. SO3 is going to be just nonpolar with LDFs. SO2 is polar but has LDFs. The LDFs on SO3, because it's O3 rather than O2, is going to be more LDFs. But with there being one lone pair on the central sulfur in SO2, we're going to have dipole-dipole, and it is going to be predicted that SO2 would have stronger intermolecular forces. Between HF and HBr, they're both polar, so they both have LDFs. Br is larger than F, therefore the LDFs in HBr will be more. They're both polar, so they both have dipole-dipole. You get a dipole arrow pointed towards a more electronegative element. And here we can see hydrogen covalently bonded to fluorine, which is a sign that we have hydrogen bonding present. When we have hydrogen bonding present, that's going to be a very strong intermolecular force. Hydrogen is covalently bonded to bromine, which does not fit our rule for hydrogen bonding. Therefore, HF would be expected to have stronger intermolecular forces. We get to E, and they're both polar, so they both have LDFs. Well, actually, everything has LDFs, so they both have a dipole-dipole. They're approximately the same size. You could argue that CH3OH has slightly more LDFs just because it has an extra hydrogen, but one hydrogen isn't going to significantly change the LDFs. However, that extra hydrogen that we see is bonded to an oxygen covalently, which is an indication that we have hydrogen bonding. Notice we do have hydrogen and oxygen in H2CO, but they're not actually covalently bonded, and so this one does not have hydrogen bonding. So we would anticipate that CH3OH has larger intermolecular forces. And then I'm going to stop here after F. There's going to be some more that upon my return we can finish together. We have these large molecules of hydrocarbons. They're not true hydrocarbons, but they look like this. And then we see H2N, carbon, carbon, and then NH2. And what letter F is trying to get at is that they both have hydrogen bonding. So they're both going to have LDFs. They're both dipole-dipole. Remember, hydrogen bonding is extreme dipole-dipole. But more hydrogen bonding is going to be present in our second compound, and more hydrogen bonding is going to yield stronger intermolecular forces. So we would expect that second compound to have the stronger intermolecular forces.